Are you looking for an adventurous summer job? Well, how about hunting invasive Burmese pythons in the Everglades?
In 2011, a team of researchers from the U.S. Geological Survey and the University of Florida published results from an experiment that had, on paper, looked promising. Build a trap baited with a live rat, place it in an area of the Everglades known to be crawling with Burmese pythons, and see how many snakes it could catch. Over more than 6,000 trap nights working in an area east of Everglades National Park called Frog Pond, the traps caught exactly 3 pythons. When researchers later disked the same ground with heavy farm equipment specifically to flush out and count every snake actually present, they found 11 more pythons that the traps had missed entirely. It was not the breakthrough anyone had hoped for, but it became one of the most cited studies in the ongoing search for a python control method that could actually work at scale. Before we get into how that happened, if you're into real, deeply researched nature stories like this one, hit like, drop a comment, and subscribe now so you don't miss the next one. The broader context surrounding this trial matters for understanding why researchers were willing to test something as simple as a rat in a box against a species already causing millions of dollars in ecological damage. By 2011, Burmese pythons had already been confirmed breeding across thousands of square kilometers of South Florida, consuming a wide range of native vertebrates and contributing to documented population crashes among mid-sized mammals throughout Everglades National Park. Yet despite the scale of the problem, wildlife managers had remarkably few validated tools available to actually remove pythons from the landscape at the time. Human searchers, still the primary removal method, were limited by the sheer difficulty of visually spotting a camouflaged, largely nocturnal snake across dense, often flooded terrain. A trap that could work passively, day and night, without requiring a trained searcher physically present at every moment, represented a genuinely appealing alternative if it could be made to work reliably, which is exactly what made this trial worth running and worth publishing, regardless of how the results ultimately turned out. To understand why researchers thought a live rat might work as bait in the first place, you need to understand what Burmese pythons in the Everglades actually eat. Since establishing a breeding population in South Florida sometime before 1985, pythons have consumed a huge range of native wildlife, but rodents make up a significant, reliable part of their diet, particularly for smaller and mid-sized snakes. Rats are also, unlike larger prey such as deer or alligators, small enough and safe enough for researchers to actually work with directly in a trap design, making them a logical starting point for anyone trying to build a lure a python could not resist. The research team, led by USGS biologist Robert Reed, alongside colleagues including Kristen Hart, Gordon Rodda, and Frank Mazzotti from the University of Florida, designed 2 different types of attractant traps, each built around the same core idea: a live rat kept safely separated from the trap's main compartment, serving as visual and scent bait to draw a python inside, where a one-way entry mechanism would then prevent the snake from escaping once it entered. The rat itself was protected throughout the trial in its own secure section of the trap, never placed at risk of actually being eaten, since the goal was luring a python close enough to trigger capture, not feeding it. The team selected the Frog Pond area specifically because previous python removal efforts had already documented a substantial resident population there, giving researchers a location where, if the traps worked as intended, results should show up relatively quickly. Over the course of the trial, they deployed traps across more than 6,000 cumulative trap nights, a standard wildlife research measure combining the number of traps in operation with the number of nights each trap was actively deployed, while simultaneously running standardized visual surveys across the same area to compare how many pythons researchers could spot by eye against how many the traps actually caught. The 2 trap designs tested in the study also differed in ways worth understanding, since comparing their relative performance was one of the trial's specific goals. Both relied on the same basic principle: a live rat held securely in a separate compartment to serve as attractant, paired with a one-way entry mechanism intended to let a curious python in without letting it back out, but they varied in overall size, entry design, and placement strategy across the study site. Testing multiple trap variants simultaneously, rather than committing the entire research budget to a single design, reflected standard practice in wildlife control research, allowing the team to gather comparative data on which structural choices performed better even within a single, modestly successful trial. Information that later researchers designing improved traps could draw on directly rather than starting entirely from scratch. Reed's team also documented the specific mechanics of how each trap functioned during deployment, details that later researchers building improved versions relied on directly. Both trap designs used a funnel-style entrance built to allow a python's head and forebody to push through relatively easily while making backward retreat far more difficult, a design principle borrowed from techniques already established in general reptile and small mammal trapping. Traps were checked daily throughout the trial, both to record any successful captures promptly and to ensure the live rats serving as bait remained healthy and were rotated with fresh food and water on a regular schedule, standard animal welfare practice for any research involving live bait animals in the field. The results, when the trial concluded, were genuinely underwhelming relative to what the researchers had hoped for. The traps captured 3 pythons total, alongside 69 other animals representing a range of native rodent, amphibian, and reptile species that had also been drawn in by the bait or wandered into the traps incidentally. To get an independent measure of how many pythons had actually been present in the study area the whole time, researchers arranged for the entire trapping site to be disc harrowed, a heavy agricultural technique using a tractor-drawn implement to till and expose the ground surface, specifically to flush any remaining snakes into the open where they could be counted directly. That follow-up operation turned up 11 additional pythons in the same area the traps had been operating in for months, along with large numbers of rodents, strong evidence that the traps had captured only a small fraction of the pythons actually present and available to be caught. Robert Reed, the lead author on the study, has spent much of his career studying exactly this kind of problem: how to measure and improve control tools for invasive snakes in general, not just Burmese pythons specifically. Much of his earlier work focused on brown tree snakes on Guam, giving him direct hands-on experience with the same fundamental challenge before he ever turned his attention to Florida's python crisis. That background shaped how the Frog Pond trial was designed from the outset, particularly the decision to pair trap deployment with an independent verification method rather than simply reporting a raw capture count and calling the study complete. Researchers who have reviewed the broader invasive snake control literature since have pointed to this study specifically as a model for how control tool trials should be conducted and reported, even though, or perhaps especially because, its own headline result was modest rather than dramatic. The disc-harrowing follow-up deserves a closer look, since it represents an unusually rigorous validation step that many wildlife control studies never bother to include. Most trap efficiency studies simply report however many target animals were captured and stop there, leaving the crucial question of how many animals were actually available to be caught in the first place largely unanswered. By physically tilling the entire study site with heavy equipment specifically to flush out any remaining snakes after the trapping phase ended, the research team gave themselves an independent, on-the-ground count of the area's true python population, something close to a ground truth measurement rather than an estimate. Finding 11 additional pythons in ground, the traps had been actively working for months, turned what might otherwise have been read as a cautiously encouraging 3 python result into a much more sobering statistic. The traps had captured roughly 1 in 5 of the pythons confirmed present in the immediate study area, a genuine measurement of trap efficiency rather than a simple raw capture count that could easily have been misread as more successful than it actually was. The research team's own published conclusions were candid about what this meant. The trial, they wrote, had captured a relatively small proportion of the pythons that appeared to be present in the study area, though they noted that capture rates for this kind of trap have historically improved with continued testing of alternative designs in other contexts. They also floated a specific explanation for the trap's limited success during this particular trial. Extremely high local prey abundance in the area at the time may have given wild pythons so many other, easier food sources available that a caged rat inside an unfamiliar trap structure simply wasn't competitive enough to reliably draw them in. It's also worth understanding what high local prey abundance actually meant in practical terms at the Frog Pond site during the trial period. The Everglades region east of the national park supports substantial populations of native rodents, marsh rabbits, and other small to mid-sized prey animals that make up a python's natural diet, and researchers noted that conditions during the study window appeared to offer wild pythons an unusually rich buffet of alternative food sources scattered naturally across the landscape. A single caged rat, however enticing in theory, was competing against an entire ecosystem's worth of easier, more naturally distributed prey. animals a python could hunt using its normal ambush strategy without ever needing to investigate an unfamiliar wire structure sitting in unfamiliar terrain. That dynamic illustrates a recurring theme across nearly every python control method researchers have tested in the years since. Any tool relying on artificial bait or lures has to compete directly against whatever natural food sources happen to be available at that particular place and time, a variable that shifts constantly and is difficult to control for in any single field trial. Importantly, the study also found that the traps posed minimal risk to non-target wildlife, meaning the 69 other animals captured alongside the 3 pythons were not harmed in ways that raised serious ecological concerns, a meaningful finding in its own right for any control method being considered for wider deployment across sensitive habitat like the Everglades. The 69 non-target animals captured during the trial are themselves a useful data point often overlooked in favor of the headline python numbers. That group included a range of native rodent, amphibian, and reptile species, drawn in by the same rat scent and visual movement meant to attract pythons, evidence that any bait-based trap operating in a habitat this biodiverse will inevitably interact with far more than just its intended target species. Documenting that non-target capture rate and confirming it caused minimal harm to the animals involved mattered directly for whether regulators and land managers would ever consider approving this kind of trap for wider use across sensitive protected habitat like Everglades National Park, where any control method has to be weighed not just for its effectiveness against pythons, but for its potential side effects on the native species conservationists are ultimately trying to protect in the first place. What this study captured most clearly, beyond its modest python count, was a broader and genuinely important lesson about just how difficult Burmese pythons are to control using conventional wildlife management tools. The researchers themselves framed their results this way, describing the trial as illustrating many of the challenges involved in testing and interpreting control tools for a large cryptic predator like the Burmese python. Pythons rely heavily on camouflage, patience, and largely nocturnal, secretive behavior to hunt successfully. The exact same traits that make them so effective as predators in the first place also make them extraordinarily difficult for any single detection or capture method to reliably locate, whether that method involves human searchers, dogs, radio-tagged scout snakes, or a live rat sealed inside a wire trap. A closely related body of research on a different invasive snake helps put Florida's rat trap results in useful perspective. On the Pacific island of Guam, brown tree snakes, introduced accidentally after World War II, have caused their own well-documented ecological disaster, driving numerous native bird species to extinction and costing the island significant amounts in power outages caused by snakes climbing into electrical infrastructure. Researchers studying brown tree snake control on Guam have spent decades refining trap designs, many of them also relying on live prey or scent-based attractants, and have documented similar patterns of inconsistent capture efficiency depending on local prey availability, seasonal conditions, and individual snake behavior. That decades-long body of research on a chemically and ecologically similar problem gave the Florida team a body of prior knowledge to draw from when designing their own python traps, and continues to inform trap refinement efforts for both species today, even though neither snake has yet been brought under control using traps alone. This 2011 trial did not end the search for trap-based python control, and its results directly informed the tools that came afterward. Researchers studying invasive reptile control more broadly have continued refining attractant trap designs for other species, including similar rat-baited trap systems adapted for controlling brown tree snakes on Guam, where comparable challenges around trap efficiency and target species capture rates have been documented and studied for decades. Within Florida specifically, the modest results from the rat bait trial were part of a broader body of evidence that ultimately pushed python control efforts in Florida toward the methods researchers eventually found more effective at scale, including radio-tagged scout snakes released during breeding season to lead searchers directly to reproducing females, and, much more recently, robotic decoy rabbits designed to lure hunting pythons into range of remote-monitored camera traps. Frank Mazzotti, one of the study's co-authors and a longtime University of Florida wildlife ecologist based at the Everglades field station, had already spent years studying the python invasion's broader ecological effects by the time this trial ran, work that later fed directly into some of the population estimates and impact studies cited throughout Florida's python removal programs today. His involvement placed the rat trap trial within a much larger continuous research effort centered at the university's Fort Lauderdale Research and Education Center, one of the primary institutions that has coordinated python science across nearly every method Florida has tested since, from early trap designs like this one through the Scout Snake telemetry program, and most recently, the robotic rabbit decoys deployed starting in 2025. That single field trial became part of a much longer chain of experiments stretching across the following decade, each one narrowing down which tools could actually compete against a predator built almost entirely around not being found. Every trap, every scout snake, every camera-linked decoy that came after it in the Everglades owes something to the 6,000 trap nights, 3 captured pythons, and 11 more discovered waiting in the same ground. The traps had been working the whole time. If you enjoy real, verified stories from the wild edges of nature, like this video, leave a comment letting me know what you thought and subscribe for more. I will see you in the next one.